because there are millions of organic compounds, and organic chemists synthesize new compounds every day. Other scientists discover new organic compounds in living systems. The goal of much of their work is to find new compounds that will solve problems and meet human needs. Better health, a safer food supply, a cleaner environment. Many of the millions of known organic compounds have the same formula but different chemical and physical properties. These compounds are called isomers. The two molecules we see here are examples of isomers. Butanol and diethyl ether have the same chemical formula, but the atoms are bonded in a different order, giving the two molecules very different properties. Butanol has a boiling point of 117.2 degrees Celsius and is used as a grease dissolver, and isomers exist among all classes of organic compounds, including the hydrocarbons. These compounds contain only the elements carbon and hydrogen. Many of the common fuels are hydrocarbons or mixtures of hydrocarbons. Methane is found in natural gas. Butane is the liquid fuel in lighters. Not all hydrocarbons are straight chains of carbon atoms. Some hydrocarbons, since organic molecules are so varied and so numerous, chemists use functional groups to classify them. A functional group is a specific combination of bonded atoms that reacts in a characteristic and predictable way. Alcohols and ethers are examples of functional groups. Butanol is an example of an alcohol. All alcohols have the functional group OH. Diethyl ether is an example of an ether. All ethers have an oxygen atom bonded to two carbon atoms. Because the molecule's reactivity depends on its functional group, we often use a generic symbol for the rest of the molecule. A generic alcohol is designated ROH, where R can be any collection of other atoms. A generic ether is written ROR'. The two carbon groups on either side of the oxygen atom might be the same as in diethyl ether. Let's explore two additional oxygen-containing functional groups found in biological molecules, aldehydes and ketones. An aldehyde functional group contains a carbon atom that forms two bonds to an oxygen atom. The carbon also forms a bond to a hydrogen atom. A ketone is similar to an aldehyde. Carboxylic acids and esters are biologically important functional groups containing two oxygen atoms. Carboxylic acids have a carbon atom containing a double bonded oxygen and an OH group. Carboxylic acids, like all acids, are hydrogen ion donors. They can ionize to give a carboxylate ion and a hydrogen ion. The hydrogen ion can act as an acid and combine with other bases that might be present. Esters are similar to carboxylic acids, except that there's a second carbon-containing group on the single bonded oxygen rather than a hydrogen atom. Esters don't have an ionizable hydrogen atom, so they have different properties than carboxylic acids. Now let's look at a couple of functional groups that contain nitrogen, amines and amides. Amines contain nitrogen bonded to 1, 2, or 3 carbon atoms. Amides are similar, except that the carbon atom next to the nitrogen also contains a double bonded oxygen. As we'll explore in detail later in the course, the amide functional group is very important in proteins. Like amines, the nitrogen can be bonded to 1, 2, or 3 carbon atoms. The presence of the double bonded oxygen in amides, let's consider some sulfur-containing functional groups. Thiols have the generic structure RSH. They're a lot like alcohols, except they have a sulfur atom instead of an oxygen atom. Sulfides have the generic structure RSR'. They're similar to ethers, except we'll finish up our discussion of functional groups with the phosphoesters. They're one of the most important functional groups in living systems because of their role in meeting a cell's energy needs. Phosphoesters are organic derivatives of phosphoric acid. We can replace 1, 2, or all 3 of the hydrogen atoms with carbon-containing groups. Thus, there are 3 kinds of phosphate esters: just as there are 3 kinds of amine. Let's take a closer look at the structures of salicylic acid and acetylsalicylic acid, aspirin. Like most biological compounds, these substances contain more than one functional group. Both molecules contain a carboxylic acid group. At the next carbon in the ring, salicylic acid has an alcohol group, OH.